Welcome to ETAP webinar, Directional Overcurrent Protection of a Wind Farm Collector System. This is Muhammad Zadeh. I'm a Principal Electrical Engineering at ETAP. In this webinar, I'm going to introduce a typical wind farm collector system, how the directional overcurrent protection is applied for collector protection. We look at a current characteristic of wind generator types 3 and 4. We also go through the reports regarding the false tripping of directional overcurrent protection. We simulate those false tripping conditions in ETAP. And then we look at the proposed solution, which are utilizing and carefully setting a flexible directional element, or also securing directional element by load encroachment element. We simulate both solutions in ETAP and we look at the pros and cons of these two approaches. And finally, we'll summarize this presentation. In a typical wind farm collector system, wind turbines are spread out all over the farm and are interconnected via a distribution voltage level system such as 34.5 kV, also known as a collector system. The length and size of the cables varies due to the radial nature of the connection. Also, each wind turbine generator is connected to the collector system through a step-up transformer. Each collector is protected by a directional overcurrent protection. This directional overcurrent protection can have phase and ground protection, but for this webinar we're going to focus on the phase directional protection, which is prone to error and false trip. So in a typical wind turbine generation, each wind turbine has some level of auxiliary load, which is typically around 20% of the rated value. So in the typical wind farms, again, in directional overcurrent protection, the pickup for the phase overcurrent protection is typically set to 120% of auxiliary load. And as I mentioned, the auxiliary load is about typically maximum 20% of rated. So in this case, the pickup is set to 24% of the rated value, which is less than the rated value. So the relay is picking up during the normal condition. However, it's blocked by the directional protection as wind turbine is supplying energy and power to the grid. So it's in the reverse direction in a normal operation. Another reason that the pickup is also set less is to basically make the relay more sensitive, because these are cables and the chance of having high impedance faults are more, and this helps to bring down the basically the incident energy and arc flash energy to protect people who are doing service in the field as well. Here is another figure showing the different type of protections for the cables, for the wind turbines. So as you see here in the right figure, typically there are two types of fuses, expulsion type and the regular fuse, current limiting fuse, to protect the transformer and WTGs for the fault downstream of the fuse. Also, as you see, there is a directional overcurrent protection to protect the collector from the fault inside on the cable. And the way that the system is coordinated, we make sure that our phase overcurrent relays are coordinated with the fuses and their curves are above the fuse characteristic in this case. Now, we also need to look at the current characteristics of the wind generator type 3 and type 4. Machines with the type 3 and type 4. Type 3 is known also as a doubly fed induction machines. As you see, I have a typical block diagram of how the WTG type 3 is connected to the system. The rotor is connected to the system through power electronics, which basically allows us to control the active and reactive power. In type 4, the wind turbine is completely isolated from the system by AC to DC and DC to AC converters, which is also known as a DC link. So this type 4 also gives a full capability to control active and reactive power in the normal condition. When you're looking at the different type of the capability curves for the wind turbine generations, in the early generations the controller was made in a way to minimize the amount of reactive power support as the active power drops. But in the newer generation, especially when there is a inverter in between of the WTG and the system, the full reactive power support is still available at zero or no active power generation. So this is kind of a D shape, as you see that in even zero active power you have all your reactive power support. So in this case, this reactive power support, as we'll see, that is going to create some challenges for directional phase protection, overcurrent protection. Now let's start with the current characteristic of WTG type 3. First, we are going to look at the current characteristics from the wind turbine generation perspective, and then we are going to look at it from the directional relay in the right hand side. So we take the voltage as a reference, and in this case the right hand side and the current would be the y-axis. In this case, the right hand side, the first quarter and fourth quarter, represent the active power greater than the auxiliary power, and the left hand side represents the active power or the power generation by the WTG, wind turbine generator, less than auxiliary power of the WTG. So in this case, if the WTG, if the wind turbine where the current direction is towards the system outgoing, if the current is leading the voltage but it's outgoing, it means that WTG is like an inductor, so it's kind of absorbing reactive power. So this is kind of against the convention of the inductor because current is outgoing. Now if the current is lagging the voltage, this is the outgoing current lagging the voltage, the WTG behaves like a capacitor, so it's injecting reactive power to the system. Now when we look at it from the wind turbine generator perspective, everything gets reversed. Basically the current gets reversed because we are looking at a different polarity, or we are looking at a different angle. So in this case, again, from the directional perspective, we are mirroring everything with kind of towards the origin. So in this case, the right hand side would be the power generation less than the auxiliary power, and the left hand side would be the power generation greater than the auxiliary power. And the second quadrant would be capacitive, because here was the fourth quadrant. Again, we are reversing everything towards origin because the current got reversed. And the third quadrant becomes inductive. So if the current is in the third quadrant, means that the WTG is generating more than the auxiliary power, and it's behaving like an inductor, means it's absorbing reactive power. The same thing with the fourth quadrant. So the third and fourth quadrant is the inductive regions, and first and second quadrants are the capacitive regions, where the WTG is injecting capacitive power to the grid. So again, looking at here, we reverse the current, so we are basically negating the current in this case. Now let's look at it from the impedance perspective. Many relays actually do the directionality or do impedance measurements for the directionality. So we look at the IV, which is more of an admittance perspective. Now let's look at the impedance perspective in this case. So if I have a voltage and my current is lagging the voltage in this case, we learned that this is an inductive nature with perspective of the directional relay for WTG. So it's an inductive nature. And if we go to the first and second quadrant, it would be capacitive. Now, when we look at a directional relay, when we look at the impedance characteristics, what's going to happen is that if the current is lagging, the impedance is voltage divided by current. So the current actually goes to the denominator for the impedance calculation. So the impedance actually would be in the first quadrant if the current is in the fourth quadrant. So basically in this case, if I have this current here, and because current is a denominator, the higher current means the smaller impedance. So this current here represents this impedance in the right hand side. For this current here, the small current lagging few degrees, what happens is that when this is in the denominator, when it comes to numerator, it becomes minus few degrees. So in this case, this current here, when it's translated to the impedance, because the current is small, becomes a larger impedance and fewer degree here. So that's basically represent this angle. So it's basically kind of mirrored with the x-axis. This current becomes this impedance, this current becomes this impedance. And now if I have a current that is capacitive, then it becomes a larger impedance, basically inductive, or it comes to basically if it's a capacitive here, it's going to be capacitive here, but it's going to go to the fourth quadrant. So when we look at a impedance characteristics, what's going to happen is that if WTG is inductive, so what's going to happen, the impedance that we see is going to come into the first and second quadrant. But if it's if it's inductive, when the WTG is inductive, the impedance would be in the first and second quadrants. But if it's capacitive, the seen impedance will come into the fourth and third quadrants. So when WTG behaves like an inductor, when there's an over voltage on the system. So if the WTG is not connected and there's an over voltage, and once we connect WTG, it behaves like an inductor to bring down the voltage. When there is an under voltage in the system, when the system needs reactive power to basically increase the voltage at a bus, WTG behaves like a capacitor type 3 and 4 and injects reactive power system to bring down the voltage. In those cases, the impedance measured by the relay is going to be in the third and fourth quadrants. Now, going to the third and fourth quadrant or going between 1 and 2, it depends on how much the WTG is generating as compared to the auxiliary power of the WTG. Now, in a typical directional overcurrent relay, the characteristics for tripping, when we are looking at the IV, current and voltage graph, is more like this. It basically covers all the fourth quadrant and a little bit of the first and third quadrant. While when we look at the impedance characteristics, we always cover the first quadrant and a little bit of the second and fourth quadrant. So that's a typical directional overcurrent characteristics for the Veen form collector protection. Now, as you see here, we see the seen impedances has a potential to fall within these characteristics and create a false strip. Clearly, you see that here. If the seen impedance falls anywhere within these characteristics, there would be a trip. But there is always a pickup. So if the current is greater than the pickup and it has the angle between, let's say, -15 to 120, then the relay is gonna trip. So as you see here, there's a good potential that for some cases the relay trips. Now let's look at it from the other perspective. What I have done, I've done some simulation, which is more of a theoretical simulation using MATLAB, showing that for 10% auxiliary power, so I assume that the WTG has 10% auxiliary power with an 85% lagging power factor. And in this case, let's assume that WTG is generating no active power. There is no wind blowing. WTG is only providing reactive power support to the system. Now, as you see, as the reactive power support increases, basically what I'm trying to do, I'm bringing down the voltage on the utility side and let the WTG inject reactive power to the system or absorb power to the system. When the WTG behaves like an inductor, basically is absorbing reactive power, we are going through this first quadrant. So as I increase the reactive power support, as you see, the scene impedance comes and enters to the first quadrant close to the origin. Blue line here, the blue circle, is a pickup level for the directional overcurrent relay. So as the red points, which is the locus of the scene impedance, enters inside the blue circle, means the current is above the pickup value. Now for these points, all these red points inside this oval, as you see here, we are in the first quadrant. The angle is about -30 to +120 degrees within the directional characteristics, and the current is above the pickup. So that's the region that if the impedance falls, the relay is going to trip. While there is no fault on the system and there is no generation, it's just reactive power support of the wind turbine generators. Now on the capacitive side, as you see, we enter the inside the fourth quadrant when the angle is more than 40-50 degree in the fourth quadrant. So this means that if typical directional relay is between -30 to 120, this region is not any danger. As for basically angles close within that range, the current is less than a pickup value. As the current becomes more than a pickup value, what's going to happen is that the angle is way below that 30 degree. Now if we look at another case where the power generated by WTG is greater than the auxiliary power. So in this case, my auxiliary power is 10%, while my wind turbine generation is 20%. So it's 30% basically is the net generations by the system, by the farm. So in this case, the scene impedance would be in the second and third quadrant, the left hand side of the plane. So in this case, if the WTG behaves like an inductor, means it absorbs reactive power in case of an over voltage in the system. As it tries to be more and more basically absorbing reactive power, the current increases, and we may actually enter the region between 120 degree and 90 degree in the second quadrant, which would be dangerous for a typical directional overcurrent relay. So this region is a region that the current is above the pickup and the angle is within the region that directional overcurrent protection may trip while there is no fault in the system. As you see, for the capacitive part is falling completely in the third quadrant, which is completely a reverse fault, so it's not a danger to the collector protection. Now let's look at another case where the power is way above the auxiliary power generate. Let's look at another case where the wind turbine generation, in this case is 80%, is way above the auxiliary power, which is 10%. And as you see here, the current is way above the pickup current, which we set to about 24% of the rated. You're generating about 70% net. So in this case, as you see, the scene impedance may get very close to 120 degree. Okay, and that could be dangerous because we are very in the boundary of the forward protection, and also the current is above the pickup, and there could be a chance that the directional overcurrent protection also give us a false trip at this region. So as you see, there is a good potential. Theoretically, we showed that, mathematically and theoretically we showed that there is a potential for false trip in wind turbine generation protection. Several false tripping have been reported in the literatures, especially these two in winter 2010 in wind farm in Texas trip. I've also listed for you the paper that you can look at it, and they have provided all information about what happened and how the phase directional overcurrent relay maloperated. Also, there is another one in Colorado Highlands wind farm where the directional element also tripped for basically normal condition, load current condition, And you can go through these two papers and look at what has happened. But basically what I explained cover the issue. And now we are going to look at the solution. Before looking at the solution, let's go to ETAP and basically simulate both scenarios and see what happens. So here I have a model of a real wind farm in ETAP. As you see here, I have my substation with the 1, 2, 3, 4, 5, 6 collector. As you see, each feeder collects power from several WTGs from the system. What I have done, I have expanded one of them in the one line diagram while the others are in the composite network. Just for the sake of clarity, I've done that. So each collector, as you see, has its own several WTGs with a step-off transformer, all the protections, cables, fuses, and connected to the system. And at each collector, we have basically a current and voltage transformer and protection relay. Here in this case, I have put 4 relays because I would like to compare 2 different solutions and the typical values and the fixed values for one vendor and for another one, so we can go through this and compare that what's going on. So now what I'm going to do, I'm going to basically plot the characteristics of one of the relays here. This is a ABB feeder protection 630. So what I have done here is that I'm plotting the phase directional overcurrent protections, and the default settings for this relay, we can go through the settings here and look at those settings. The line angle is 62 for this cable, for this system, so I keep it at 62, and I left the other settings as default. So for this relay, the maximum forward angle is 75 degree, means that this side is going to go up to 137 and the other side is 80. So in this case would be 62 minus 80, which would be minus 18 degrees. So I have minus 18 degree here and about 38 degree here. Those are the default values, so I didn't touch them, so we can use them for now. Now what I have done, I have actually increasing the or decreasing the voltage on the utility side. In this case, first I'm starting from 95% voltage on the utility side and increasing the voltage to 110 and see what happens. And at the beginning, my WTG generation is 0 and my auxiliary power is about 10%. So let's just start with the 95% voltage. So when we start with a 95% voltage on the utility side, as we mentioned, the seen impedance that we expect from the system, WTG will behave like a capacitor. So when it behaves like a capacitor, as we mentioned, the seen impedance would be in this area. 95% is a low voltage, so WTG tries to inject lots of reactive power, so the seen impedance comes in this side of the system, and this is what you see in ETAP. Now if we go to the 97%, I have done all these analysis beforehand, so I'm just demonstrating here. Now we go to 97%, the WTG injects less reactive power to system, less capacitive, so angle comes a little bit higher. We go to the 100% voltage, we are at a set point. So in this case, as you see, the WTG behaves a little bit capacitive because we have an auxiliary power that it was a little bit inductive, so it tries to compensate that to maintain the voltage at 100%. So in this case, you see that we are within the characteristics of the directional overcurrent protection, but because for this case the impedance is about 219, basically the current is less than a pickup current, so the relay actually does not trip. Now let's increase the voltage to 103. So in a 103, again, as we go through the higher voltages, the WTG behaves like an inductor. So the impedance goes into the first quadrant and gets, as we increase the reactive power, it gets close to the y-axis. So a relay does not operate. The circle here like that means that it's not tripping. So stays in the forward direction, but is not tripping in this case, means that the current is less than the pickup current. So now if I go to 105, probably still the current is less than the pickup value and is not picking up, it's not tripping. Now if I go to 106, means 6% over voltage on the system, still is the same case. Now if I go to the 7%, you see that the relay actually trips at 7% over voltage, and you can see the trip time of the relay, which is 9 seconds and 29. So from the OLV also, what you can do is you can look at the current. For the overcurrent relay, the pickup value is set to 180 ampere. So if we go to the 105, in this case, I need to run 105 to look at the current. So what I can do, I can go here and run the 105. Run. I've set up a scenarios for each case, for each overvoltage condition. So in this case, you see that the current is 150, still is less than 180. If I go to the 107, or let's try 106 first. In case of a 106, the current is about 170, so still is less than a pickup, so it doesn't trip. Now once we go to the 107% over voltage on the utility system, the WTG try to inject, basically absorbs more reactive power. The current goes to 190 amperes, so the relay is actually going to trip. The current is above the pickup, the trip time about 9 seconds. So as you see here, there would be a false trip for no fault in the system. This is just a regular load flow, but there's an overvoltage on the system, and WTG, it behaves like an inductor. It wants to absorb lots of current, reactive current. So it behaves like a fault actually in this case. But the reason is that the pickup level is low to be more sensitive, but that causes the false tripping issue. Now if I go to 108, is the same scenario. 109, 110. So as you see, the impedance gets closer to the origin. What I have done, I've created a graph with all of them for you. I put a crosshair in our plot to show that where is the pattern of the voltage. So at 95% we are here, 97%, 1 per unit, 103, 105, 106, 107 is the place that actually current goes above the pickup and it trips, and then it comes to the 110. Basically is the 10%. Typically we don't do the analysis above the 10%. For 10% over voltage we are here. So for all 7, 8 and 10%, the relay is gonna trip at the any of these. If I go to the 10%, you can look at the trip time. In this case is about 1280 milliseconds, which is about 1.3 milliseconds in this seconds. Now let's look at get back to the other StarZ view and look at, by the way, we are using a StarZ mode to do this analysis. Now let's look at the condition where the active power generated by the WTG is more than the auxiliary power. So let's start with the voltage at, I've done few cases for you guys. So let's start with, let me go to the simple one so we have no crosshair so you can easily see each one at a time. So let's look at 103, which basically 3% over voltage, and the power generated by WTG is about 25%. So it's 15% more than the, basically is 25%, while the auxiliary power is 10%. So in this case, as you see here, the seen impedance is here in the second quadrant, but it's a little bit far from origin. The seen impedance is about 262, so it's far. This means that the current is less than a pickup, so the relay does not trip. Now if we go to the 105, in the 105 with the 50% power, what happens is that the angle is about 136, and we say to 100, probably 38 it was the case. And now the current is the seen impedance minus 110. It says that the current magnitude is higher, so the current is above the pickup and the relay trips at the 29 seconds. Another case is 110%, so the higher over voltage while less power here. As you see, I'm at the 10% over voltage but generating 25% by WTG. So the scene impedance is about 109, means current is above the pickup, and in this case also you see a false trip. So this is in case of a, let's say, a relay from ABB with the default settings. And you can see also the same case in the case of a Schweitzer relay, 351 or 350 relay, or any overcurrent protection also is very similar to like 421 or other. For now I have 421 in the library, so I'm using that one, but it doesn't make any difference. We are looking at the basically TOC1 phase overcurrent relay. So in this case also, if I go to the 95%, in case of SCR relay, the directional overcurrent protection does not have that much setting. It's just the line angle that we set, which is 62 in this case, and the forward and reverse angles basically are minus 90 to plus 90. So we are covering a wide range. So that actually increases the more chance of false stripping. So at 95% we are here. At 100 we go close, again very similar to what we saw in the other relay here. We go to 105, we go up, we go to 107 is the place that basically both relays are set with the same pickup value. So both we're gonna trip at the same places at least in the first quadrant size. So 107, 108 is gonna trip, 109 is gonna trip. Now if you look at the other side, the left hand side of the graph, we look at 103P25. Again, this has a lower current, basically low pickup, so it's not gonna, basically the current is less than a pickup, so it's not gonna trip. At 103 voltage and P60, we had a tripping also in ABB relay, but very little margin. Here we have more margin here, so there will be more chance of false tripping. Then at 110 again we're gonna have trip too. So both relay, as you see, they will have a potential of false tripping. Let me also bring this graph here for, I think I didn't have a crosshair for the Z2. So now let's look at the solutions. What are the solutions? So the solution here for the ABB relay, the one that has been proposed, is to basically kind of contract the directional characteristics rather than covering some portions of the second quadrant and fourth quadrant. They try to minimize as much as possible from the fourth quadrant. So here we have a very little margin, so we didn't have that much danger here, because for the cases that happens in the fourth quadrant, the current is always above the pickup, as less than a pickup current. The more danger is in this region and also in the first quadrant. So what they have done is that they have tried to bring down the max forward reach. So in this case, as you see, we are coming close to 90 or maybe a little bit less than 90 degree. So what this does actually, it's gonna avoid the false stripping in the cases that wind turbine generates more than auxiliary, which is most of the cases. Okay, for the cases that WTG is generating less power than the auxiliary power, this is a kind of a rare conditions. So at those conditions, the WTG is not generating. Losing a generator at those cases also probably is not that much a probably issue, because there's no generations, and that's not gonna, even though that's not desired at all, so that's a false stripping and we should avoid that. But for now, the solutions that's proposed is not gonna solve the issue of the cases where there is a no wind generation, or wind generation is less than auxiliary, and we have very high over voltage on the system. Again, this is a very rare condition. Two things needs to happen at the same time. First, there should be a very little generation by WTG, should be less than a auxiliary power, and at the same time there should be a large amount of over voltage on the system to have this scenario. The cases that is more probable is the cases that we have some generations more than auxiliary, but so basically we are here in the second quadrant, and there's an over voltage on the system. As you saw that we could have a trip like in the 5% over voltage. So we can avoid that by actually contracting the characteristics, reducing the maximum forward reach. That's what proposed for the REF 630 relays, or the directional relays, where you can set. The other solution is to basically this is proposed by the Schweitzer Engineering Laboratory for the relays, is that they have a directional relay which has a fixed minus 90 to 90 degree angle. So what they have done is they have proposed to incorporate the load encroachment characteristic. So what they do, they're gonna basically cut all the second, third, and fourth zones. Okay, basically in those cases they're gonna cut, as far as the current is less than the rated current, they're gonna cut these three characteristics and block the directional overcurrent protection. So that would leave basically the characteristics to only about the first zone. So in this case, let's go to the ETAP and look at what are those proposed solutions. So now let's look at the ABB relay, the REF 630. So, and let's look at the V95 here. Let's set it like that for the beginning. So as you see here, the characteristics, let me go actually to 100. Let's set it to 100. So in 100, as you see, the characteristic is not anymore covering the second quadrant. If I click here and go look at the settings of this characteristic, now is about this is again from that paper published. So let me show you the paper. This is from this paper. The second one is covering how the ABB proposed to solve this issue. They have set the forward reach to basically the RCA to the 42 and the forward angle to 42. And mean forward angle is 43. Considering that the RCA is 42, so the max forward angle goes from the 42 to plus 42, it would be 84, and the mean angle would be 42 minus 43 would be minus 1 degree here. So this angle is minus 1, and this angle here from the max forward angle would be 84 degree. So in this case, as you see, again, we're going to have issues still for the 107. Still stripping. 108 is gonna trip, 1010, 109, they're all gonna trip because we haven't solved that issue yet. But these are very rare cases and may not happen for any wind farm. There could be cases that wind farm is basically disconnected when there is no active power. But if that's not the case, we have to mitigate the issue of false stripping in those situations. Again, it would be very rare because there should be a huge amount of over voltage on the system as well. Now, if we're looking at other side, let's say 103, we didn't have a trip, but it was in the left hand side. 103 P60, we had a trip before, but in this case we don't have to. If I go back and look at the R1 for this report, basically at V103 P60 here, as you see here, there is no trip. If I go to 105 P50, here I don't have a trip. Let's look at the other relay. The other relay, actually the original settings was tripping at 29 seconds, but the new setting is not gonna trip here. So you see that here is a circle, is not a cross, so it's not gonna trip. And the same with the 110% with the 25% generation. So again, it's not gonna tripping here. So by kind of reducing the maximum forward reach, we actually avoided the false tripping on the most probable cases where there is some level of generation more than auxiliary, but there's an over voltage in the system. Now let's look at what we have done for the Schweitzer relays. So in this case, what has been done, there is a basically we have the directional overcurrent relay, and we have set the load encroachment. So we have one load encroachment from 90 degree to 270 degree, and we have another one from 0 to minus 90. So if I go look at the load encroachment, in this case, these are our settings. So we are going from minus 90, 0 to minus 90 this side, and we are also blocking 90 to 270. So in this case, what has happened, we have put a logic together that relay, the 51 relay, is gonna trip if there is not basically detected or is not tripped by the load encroachment. So it's not picked up by load encroachment. So in this case, what happens is that if the fault seen impedance happens somewhere here or somewhere here, is going to be blocked by the load encroachment. Now let's look at some cases here. That let's say the V1025 is the case that we had a trip before. So in this case, as you see, I'm plotting two things here. I'm plotting the TOC element is going to trip by itself. This is a protection element, but load encroachment also detect that, so it's going to block. So in this case, if we look at actually the output of this element, let me go to the plot manager to plot these two signals and look at what happens here. If I go to the V100, this one was a trip, and we look at a new relay by SEL. So in this case, I'm gonna plot the TOC1. Let me see, I make sure that I'm plotting the TOC1. I'm plotting the load encroachment. So let's go and pick the load encroachment. Okay, load encroachment would be ZL out. So both of them, I'm gonna pick both of them. And trip signal as well. So let's plot these three signals. So as you see, I have an inverse time characteristics that's tripping about 2.2. But load encroachment already picked up, and it's going to block the overall protection, so there won't be any trip signal at all. So what happens here? There is a detection by the overcurrent element, but the load encroachment element also picks up and is going to block the tripping and false tripping of the relay. So in this case, relay is not going to trip because the load encroachment picked up. So that's basically the solution, but still the same issue with the ABB relay, that if there is that rare condition where there is an over voltage in the system and voltage is very high, 9%, 8%, then what's going to happen is that in this case, as you see here, load encroachment is not going to block and relay is going to trip. So in this case, as you see here, if I remove that, relay is going to trip because there's nothing else to actually block the signal. So that's again the issue. In the paper proposed or published by the people, both this paper and another paper from SCL as well, a Schweitzer paper, they're recommending is that there's maybe using a direct line current differential protections and other solutions for the beamform collectors as well. So again, what is important is do this analysis, make sure that we set the angles carefully, look at the over voltages in the system, and do the analysis, make sure that everything is fine. These rare conditions can also be avoided by increasing the pickup, but that's going to reduce the sensitivity. So there would be a kind of we need to do a balance, that how sensitive we want our phase overcurrent protection to be, but at the same time make sure that it doesn't trip for the over voltage in the system. We also need to look at the capabilities, the wind turbine capabilities, to make sure that what kind of reactive power support is available, and when we go to the zero power, is the full reactive power is available or not. So all those kind of things can be incorporated as part of the ETAP projects to do the study in the StarZ mode, to make sure that the directional overcurrent protection element is reliable and there won't be any false trip in the system. Let me summarize my webinar at the end. We talked about the typical beamform collector system and how the phase directional overcurrent protection is applied, and then we look at the current characteristics of wind turbines, type 3 and 4, and we discussed that they can provide full range reactive power support. They can go all the way from capacitive to inductive, and they can do that even when there is no power generation. That can create a case that from the directional relay overcurrent perspective, when there is very little active power generated by the WTG, the impedance seen or measured by the relay will be very similar to the fault. So it's going to fall within the first and second quadrants. That can create a fault stripping, as it has done before in the field. We discussed about 2 papers that actually reported that scenarios. We simulated those fault stripping in ETAP. We used the StarZ mode to basically set the relays and create some views to look at the characteristics, that how basically the seen impedance moves as the voltage changes in the system, and the reactive power supports by the WTG changes to maintain the voltage at a set point. So we showed that in 2 conditions this fault stripping can happen. Number 1 is when the powers generated by wind turbines are very little, less than the auxiliary power, and there is an over voltage. For the simulated case, it was above 7%, which is a very rare condition. But the most probable case is when you have some level of active power generation, 25%, 50%, while there's an over voltage in the system. So in that case also the fault stripping can happen. We simulated this for both very well-known overcurrent protections like from ABB and SCL. We look at the 2 proposed solutions presented in literature in the most recent conferences. One of them is to contract the characteristic, especially reduce the maximum forward angle to make sure that it falls close to the basically 90 degrees, so we don't go to the actually second quadrant, and also we minimize the angle on the fourth quadrant, so basically we go about 0 to 90 degree. The second solution that was by the SL is to incorporate the load encroachment elements to block the relay operations for any basically impedance within the second, third, and fourth quadrant, as far as the basically the current is less than the rated value. We simulate both proposed solution, and we show that they are successful to basically block the fault stripping for most common cases where there is active power generations. But when it comes to the no or very little active power generations, both proposed methods still suffer when there is a large amount of over voltage in the system. What is very important here is that for any system there should be a study done to make sure that, depending on what kind of reactive power sources are available, type of the wind turbine generations, the amount of auxiliary power, and settings of the relay, to minimize the potential of fault stripping. With this, I'm done with this webinar, and I'm more than welcome to any question. Thank you.